So, what are the basic requirements for these systems then? If you're going to smoke, what are the basic systems? Well, there's three essential features of a smoke ventilation system. Without any one of these, it's not going to function effectively. First of all, there must be some means of forming a smoke reservoir to prevent the lateral spread of smoke, which could result in excessively loss of buoyancy. I mean, generally speaking, malls with high ceilings or roof lights will allow a deeper smoke reservoir and hence a more effective smoke ventilation system than in very low, narrow malls. Secondly, there must be a form of extraction of the smoke within the reservoir to prevent the smoke layer building down below what you classify as the design depth. This can be natural, which is buoyancy-driven ventilation, or it might be mechanical extraction, depending on the circumstances. And the rate of exhaust must equal the rate at which the smoke enters. That's what you've got to do when you work your calculations out. Work out the extraction rate must equal the mass flow rate of smoke when a fully developed fire's gone. And if you can match that up, you've got your clear layer height, you've got your equilibrium height. And thirdly, since the gas is being extracted consistent, there's all of air, basically all of it's air mixed with a bit of smoke, fresh air must enter the mal to take place. In other words, it must enter at a rate equal to what's been taken out, because if not, you get a back pressure. It must enter at a rate equal to the rate of extraction of smoke and at a low enough height not to mix. So there's no point having your air extraction rates above the equilibrium height because it's going to draw in smoke. The air's going to come into where the smoke is. It's going to make it even worse. So it needs to be lower than the equilibrium height, well lower, and it must come in at the same rate. They are the three essential features. The most important factor with a fire, though, and which is what we're going to discuss, is time. Fires grow with time. Yeah, we know this steady state fire and growing fire. Generally, fires grow with time. Exponential fire growth. Now, because fires grow with time, and ideally all calculations then should therefore use growing fires. However, there is limited data available with fire growth rates for retail premises. In other words, we haven't got the information to work it out. We don't know the fire growth rate after time with a fire, the fire growth rate. We don't know them all. There's no data. So it's very hard to use these growth rates for different complex buildings with different things in there. You can't use them. And therefore, generally, what they'll use is what they call a steady state fire. They won't use a growing fire as the design fire because there's not enough data to work it out. What they use is a steady state fire. Now, a design fire is used which has a low probability of being exceeded, and the smoke ventilation system is designed to remove the mass flow rate of smoke necessary to maintain clear conditions in the mal for escape. And it's important to remember that sprinklers in shops are an essential part of the smoke ventilation system design in order to prevent the fire growing beyond what we call the design fire size. For example, in shopping malls, you should put fast response sprinklers in. If you put fast response sprinklers in, maximum fire size should be 2.5 megawatts. Normal sprinklers, you've got 5 megawatt fire, but it limits the fire size so that you can work out the smoke rate, the smoke extraction rate, and you can make sure the system can deal with it. Now, there's other essential factors that should be borne in mind when designing a smoke control system. Now, when the mal has more than one level, it's also necessary to restrict or channel smoke on the lower levels in order to restrict entrainment into the plume rising through the upper level. For this, you got your channeling screens. Once the smoke has entered a ceiling reservoir, it will flow towards the extraction points. Now, since this horizontal flow is driven by the gas's own buoyancy, there will be a minimum depth for any particular combination of smoke temperature and mass flow rate. Because it's using its own buoyancy, it's got to have this certain amount of temperature heating it to drive it out. Now, the capacity of the extraction system depends mainly on the height of the gases when they've risen to the layer base and not at all on the area of the floor or the volume of the space. So the capacity of the exhaust system is on the height the gases rise. Doesn't matter about the area of the floor, the volume of the space, it's the height. That's the critical, and that's when all the calculations, the height of the rise of the plume is critical. It's the height. Now, some use a rule of thumb is generally 3% of the floor area is required for natural ventilation, or an air change rate such as 5 air changes per hour for powered ventilation. That's what some say is a rule of thumb for the ventilation requirements. But you can't use this. You can't use this for ventilation systems for life safety. You can't say, let's just have natural ventilation, 3% of the floor area. You can't do that. You do have to do the calculations because it's, especially life safety, property protection systems, you can't just rely on these 3% or 5 air changes an hour. They're commonly said, quoted, but you can't use them for these systems. Now, I want to discuss the impact of installing sprinklers in the atrium itself. So not just in the shops, in the atrium itself, which is not necessarily in the compartment of origin. Now, sprinklers in compartments off atria, for example in shops, as I said before, are an essential part of the smoke ventilation design in order to prevent a fire growing beyond the design fire size. As I said, fast response sprinklers, 2.5 megawatt fire. However, if sprinklers are installed in the atrium itself, then sprinkler operation will lead to increased heat loss, reducing the buoyancy of the smoke which is coming up, which in turn can contribute to progressive loss of visibility under the smoke layer. So as it goes off, if the sprinkler goes off in the atrium, it's going to start to cool the buoyant gases and they're going to possibly start to drop. However, gases sufficiently hot enough to set off sprinklers will remain initially as a thermal buoyant layer under the ceiling. In other words, for a general sprinkler head, 68 degrees. If that hot smoke is at 68 degrees and it goes off, even any local cooling, it's still going to maintain buoyancy to get out. It should still get out. It shouldn't affect it. When the fire occurs in a shop, the operation of the sprinklers in the mall will not assist in controlling it. So there's not, the sprinklers going off in the mall are not going to help a fire in the shop, are they? That's why you need them in the shop as well. Now, the problem is, if too many sprinklers operated in the atrium itself, sprinklers in the shops become less effective because obviously they're about flow rate as the available water supplies approaches its limits. So if a lot go off in the mall, then it's going to cause a problem in the actual shop itself. So that could cause a problem. Now, sprinklers are only required in the atrium itself if the fire loading exceeds 5 megawatts or a 9 metre perimeter fire. So that's the key. If it's less than 5 meg, the design fire, or a perimeter of 9 metres, you don't have to put sprinklers in the mall itself. However, the sprinklers are unlikely to operate in a very high atrium unless the fire is much larger. So even if you had a certain fire size, 5 meg, if it's a very, very high atrium, the smoke getting up there, it's not going to be hot enough to generate enough to operate the sprinklers anyway. So sometimes you can think, what's the point of having them? So you've got to be careful when you put them in. However, sprinklers could serve a life safety role by keeping the smoke temperatures well below acceptable levels. In other words, if you're going to have you've got a fire with a lot of smoke in it, and that's why you're putting the sprinklers in, and you can demonstrate that the sprinklers will be hot enough to operate the sprinklers, then you can use it as a life safety alternative where you are going to get excessively high smoke temperatures, i.e. above 200 degrees C, which is what we classify as the tenability limits for people travelling below them. Now, there's a number of problems which must be considered when putting sprinklers in the atrium itself. The first problem is, because a natural ventilation system relies on the buoyancy of the hot gases, as I said, if the cooling of the smoke by the sprinklers is underestimated, then the smoke may lose all its buoyancy and the system will fail, especially if it's close to the operating temperature. So if it's only at 70 degrees and it pops the sprinkler head at 68, well now at 70 it might lose too much buoyancy. That's the first problem. Second problem, conversely, a powered extract system to a reasonable approximation removes a fixed volume of smoke irrespective of its temperature. So that's what it does, it removes certain cubic metres a second. Therefore, if the extent of cooling is overestimated, the system could be under-designed. So if you say, well, the sprinklers are going to cool it, we're going to have this amount of smoke, you could be under-designing your system based on the fact that you've overestimated how much cooling. Now, the problem is there is a lot of information on the impact of this available. There's not a lot of information on how this works, these problems. But here is a general guide. If the smoke passing a sprinkler is hotter than the sprinkler operating temperature, that sprinkler will eventually be set off. The sprinkler spray will then cool the smoke. If the smoke is still hot enough, then the next sprinkler will operate, cooling the smoke further. Now, a stage has got to be reached when the smoke temperature is insufficient to set off further sprinklers. The smoke layer temperature can therefore simply be assumed to be approximately equal to the sprinkler operating temperature if natural ventilators are used. That's one of the guides. What's the sprinkler operating temperature? First one goes off, cools. Second one goes off, cools. Then you're looking at, it's not going to be much far off the actual sprinkler operation. That's a guide. That's if the ventilators are natural ventilators. Now, what about with mechanical ventilators? Well, with mechanical ventilators, you don't have to work out the area of the ventilators. You have to determine the volumetric flow rate of smoke. You have to work out how many cubic metres of smoke are going to come out a second. Now, when determining the volume extract rate required for fans, if you can ignore the cooling of the smoke, and this will result in the safety factor. So if you don't take it into account, it's a bit of a safety factor. Another method is to consider that the cooling and the consequential contraction of the smoky gases can be estimated on the basis of an average value between the sprinkler operated temperature and the calculated initial smoke temperature. In other words, go between them. If it's cool, it's going to contract, it's going to require less volumetric extraction rate. So like I say, if you ignore it, you're going to have a safety factor. If not, look at the temperature smoke that you've got initially. Now look at the sprinkler operating temperature, assume somewhere in between. Now, since a fire may occur close to at least one of the extract openings, whereas the other openings may be well outside any probable zone of operating sprinklers. Now, if the sprinkler operating temperature is set high enough and is above the calculated smoke layer temperature, then sprinkler cooling in the miles can be ignored. So it's not going to go off anyway. So if the temperature of the smoke is well below what the operating temperature is, they're not going to go off unless there's actually a fire in the atrium itself. Now, another topic for debate is the issue of the interaction between ventilators and sprinklers. The argument is that if the ventilator's open, then this will allow the heat to leave the compartment and affect the sprinkler operation. So if the vent's open, out goes the smoke, it won't set off the sprinklers. Well, experiments have demonstrated that there are no engineering issues raised where both systems are used in the same building. The provision of smoke vent reduces the spread of fire products throughout the building due to the release of hot gases, getting it all out, and fire material from the building. This will improve the visibility and conditions in the building for occupants to be able to escape and for firefighters to undertake firefight operations. So these ventilation systems are excellent. And generally, it is accepted that early vent operation does not have a negative effect on sprinkler performance. Where sprinklers successfully contain a fire, you could argue that ventilation may not be needed except for post-fire smoke clearance. You know, after the fire brigade got there, they come and get the smoke out. Now, these are the issues that must be considered by the designer. But as I said, there's not a problem with having ventilation systems and sprinklers working together. Generally, there's no problems. Now, that covers the introduction.